But once we've done that, then we can piece together some pieces. So this is going to be the number of stories connected to a story through trope space, right? So this is the average number. So I'm going to start here. How many average? And so that's a really crucial piece. And it's going to be from the first derivative of this induced distribution. So we differentiate it, and we have this story for it that it's a composition of the underlying degree distributions generating function and then the other friends distribution. I know this is a technical thing. So we're just going to differentiate that. That is a chain rule, right? So this blob comes out here, and then we've got the first derivative here with the function still the same, and we're evaluating at 1 because we're trying to find an average. So we have this. And so if you do it the other way around, then the average number of tropes connected to a random trope. So we start at a trope, go down to all the stories, go back up to tropes. The average number that we'll get there is going to be similar. It's going to be a flip of these things. So that's not bad, right? This is in terms of, I know this is, yeah? This is in terms of the underlying distributions. Yes, right? Yep. So, yeah, we know what these are, right? So this is the first derivative of the underlying degree distribution, which is just the average of that degree distribution, right? It's the average degree, right? It's the first derivative average degree. This is one we've worked out before, right? It's the average of k minus 1 divided by the average degree. This is the, your friend's a strange kind of story. That's what that is. And so we've got the flip of these here and here. It's quite nice. Again, that's a picture, right? So we're going to bounce back and forth. We need to really kind of get at the spreading though, so we need to be sort of moving back and forth. All right, so we'll do that. What we now need is this guy. We need the first derivative of this generating function. Evaluate at 1, right? That's going to give us the average number of other friends that we reach once if we do 2 steps, and I guess I don't have it on this slide, right? So if we're going to start a story, go up, find all the stories below it, and then go up again, and we want to see, like, if we're going towards this trope, how many new arrows to tropes do we get in 2 steps? Okay, so again, it's a derivative story. We have this composition of the underlying friends of other friends distributions. Just go through it. I know I'm belaboring lots of things here. These are using old results, right? So that the first derivative of that other friends degree distribution has this form, right? It's the second derivative of the generating function for the underlying degree distribution. That's how we got the k and k minus 1. So these 2 pieces, these 2 pieces. And you can see the symmetry here now, right? So this if we'd started with stories or tropes, it doesn't matter. Because we're talking about edges, right? So it actually should be symmetric in this case. So the symmetry is good. I know it's not true. But this is a very nice result. So this is where we get to, we're just really going to multiply the 2 gain ratios together to connect it back to some old words, right? So there's a gain ratio, right? We're going to start at a trope. How many other tropes, we're going to move towards a trope from a story. How many other stories does that lead to? And then we're going to, on average, we're going to start at a story, we're going to start at a trope, hit a story. How many other tropes does that lead to? So that's really what this is. Yeah, the notation is probably a little funny. So as long as this is greater than 1, right, then we have a giant component in both induced networks. They're different, of course. It's not that they have the average. They don't have the same average degree or anything like that. But they can be. So as soon as you get a giant component in the bipartite structure, then you get it for the induced networks as well. So that seems reasonable. So it's a product of two gain ratios. You will actually see this in early papers. This is, in fact, how it's written out. That this is the condition for a giant component in a, which is true, right? You could rearrange all of this and you'll get this structure. It's maybe mathematically a little better, but it's it's something equals 0. We need a great, honestly, this is losing a sign, which is a problem. You're not sure if it's greater or smaller than for which you have a giant component. That's been lost. The thing is, this has been derived from some limiting condition. If you remember, we looked at what was the average component size, finite component size, and that exploded around the giant component coming into existence around the phase transition. So you can say, okay, I've got some higher order measure of this system. When does it go to infinity? So you can do that, and that's just that now you're sort of playing a little bit of a mathematical game, and you get out a condition, but this is, you can't understand what this is. You maybe can't understand all the other stuff, but you can't understand what this is, right? This is, this is not clear straight away. Whereas from all the stuff we've done, this is a much clearer, this has the physics in it, right? There's a gain ratio and a gain ratio, and you have to multiply those things together to get them to be greater than 1. One of them can be smaller than 1, right? It can kind of like dip down a little bit. On average, maybe tropes are in, maybe there are a lot of tropes that just aren't even in stories, right? They're just like, these are ones that haven't been written into stories yet. Trope space is bigger than all written stories. Yeah, I like that. Okay. So, it could be that, the average number of stories that a trope is in is a half or something like that. But if you have on average, 4 tropes per story, then you're going to get a connected thing.